So we have already talked about most of these things. I told you that basically what we need to do is we need to be able to start the building with known sizes, and that's our problem, that analysis cannot be done unless you know the sizes already. We should be able to we should be able to use some kind of guidelines to estimating the sizes. Now, what are the key things that you want to know in a tall building? What are the very key problems or key properties that we have to know? Now, of course, no, not response. To start with the building, what do we need to know to start anything? We need to know primarily three things. Main. Number one, we need to know the floor system. Right? Are we going to use flat slab? Are we going to use beam slab? Are we going to use a steel structure there? What is going to be the floor system? And floor system does not really depend too much on the number of stories, because it's going to be the same, repeated everywhere. So that decision can be made almost independently to the height of the building or number of floors. Only depends on the planned sizes and planned layout of the building. But it's a very important decision because the weight of the building will depend on what system you select. And weight of the building will govern the weight of the load on the column, load on the foundation, load on the shear walls, will also govern the base shear, mold shapes, everything, mass. So mass is very important. So reducing the mass of the floor system is very important, because if you reduce the mass of the floor system, it multiplies by number of floors. So if you have 50 stories, whatever reduction you make, the advantage is 50 times, not one time. And that is why spending some time on the selection of the floor system is quite important. And there are so many choices of this floor system that we will talk about later, that it's amazing. Maybe 40 different systems are available to be selected from. Right? Not 2, 3 or 4, maybe 40 different variations of floor systems are possible, and you have to choose the one that you want. But obviously, through experience, we have found that, okay, most likely 10 will be suitable for tall building. Others may not be suitable for tall buildings for a number of reasons. So out of those 10, you may have to choose 1 or 2 and then compete them to find the right one. Okay? But again, narrowing down, experience-based, these days, 90% chances are that you will be choosing a post-tension flat slab. That's interesting, new development, right? And now more and more people, first people never thought that this is possible, and this was not a choice. Now, because of many reasons that I will explain later, post-tension flat slab is becoming a choice, possible choice, and a preferred choice by everybody. Everybody likes that so much because of its many advantages. Interestingly, the building code does not allow that to happen. So if your building is in a seismic zone, it's a high tall building, they do not allow flat slab in that building. But that is becoming the choice of most designers. Now, people, these guys, now a long time ago, 64, 73, 74, developed many systems to be used. So that is the floor system. That's one thing. Second is now the lateral system. What is going to resist your horizontal forces? Sure. Vertical forces will be resisted by floor, whatever you say, and we are saying, okay, post-tension flat slab or concrete beam slab or composite steel, there could be many options, could be selected. So that's one decision is made. Then the question is, who is going to resist the lateral forces? The problem is that in a short building, the beams which are carrying the gravity load and the slab which is carrying the gravity loads can also help in carrying the lateral load. Not in a tall building. We find that those members, you don't want to make them part of the lateral load system, because if you do, then every floor will have to be different. Because every floor, the horizontal load component is different. It's very small at the top. As you go down, the horizontal force becomes larger and larger, and because it's cumulative, right? So that means the floor slab or floor system in every floor will have to be different, which is very difficult, and the beams will have to be very big, right? Because the forces are increasing. So we don't want, now normally we do not want to involve the gravity load system to be part of the horizontal force system. So we want to find a system for the horizontal loads which is independent, does not depend or rely on the floor system, right? And that is where these gentlemen, Fazlur Rahman Khan and this Warriors and other people, they developed some nice techniques, right? We will talk about that. And then 75, they also had approximate methods of analysis for tall buildings. Now, this is the major quantity of interest to us that we need to really be careful, which is the cost of a structural system which is dependent on the weight, pounds per square foot or kilogram per square meter. That means what is the quantity of concrete per kilogram, concrete weight per square meter of the building area? What is the quantity of steel, kilograms per square meter, because that will determine the cost of the building. So when you are selecting systems, ultimately this will be something that you need to worry about. You also need to reduce the weight and the cost, because two components are interconnected. If you use more concrete per square meter, it has more weight and also more cost. And when it has more weight, more forces. So it affects everything. So reduction of this parameter is quite important in whatever you are trying to do, right? So that should be the target, to achieve a minimum weight per square meter of the floor area for whatever system we are selecting, whatever material there is going to be. Even the columns are measured the same way. Total column weight in one floor divided by the floor area, that is an indicator. Shear walls in one floor, all the shear walls in one floor divided by the floor area, that is an indicator. So ultimately the indicators become the quantities per square meter or per square foot, which relate to cost, which relate to weight, which relate to everything. So that is something that you need to quickly be able to compare right away between two systems. Then stiffness of the system is also associated with weight in a way, right? Actually the mass and stiffness will be key components for the response, right? And stiffness is associated with weight because the section sizes and stiffness are interrelated and mass is interrelated, so it's a complex problem. An ideal structural system could be the one in which the steel quantity to carry the gravity load alone could carry the wind load now, or the lateral load. Now this is an interesting statement. Ideally speaking, a system which does not require any additional steel or concrete to resist the lateral load, that means only the gravity load design system can also take horizontal loads, will be the least cost solution, because you're not adding anything for the lateral load. But obviously that's not going to be possible. But the target is something like that. So first of all, you calculate a building parameters as if there is no horizontal load, right? Just design for gravity load and you get the number, everything, cost per square meter, concrete per square meter, steel per square meter, and then you add lateral loads and you see what is the premium that you have to pay. And if that premium or that extra cost or is too high, then your system, lateral load resisting system, is not that good. So first of all, optimize the gravity system, right? And then start the horizontal system and try to keep it minimum addition, right? So these are some of the ways that you could, so these are the concepts, what you have to consider. Number one, have to keep the quantities of the weight minimum, which will reduce the cost, which will also reduce the mass, which will also reduce the forces, which will also reduce the reinforcement. It's a cycle. So we need to keep the mass low and need to keep the weight of the things low. Secondly, the premium for lateral loads should be minimal. So that's why we try to utilize what we already have to carry the lateral loads. And for that, the tubular system is found to be one of the most efficient ideas, that it almost adds nothing. Interestingly, it almost adds nothing to the gravity load system and yet takes all of the lateral load system. Extremely efficient idea, right? And that's why when our friend was saying shear wall, shear wall, shear wall, I didn't want him to jump to shear wall, because shear wall adds things to the gravity load that we don't really need. So shear wall may not be the most economical, suitable, best option to go for a tall building, but often is the easiest one to use, right? So optimization, formulate design objectives, so on, structural modeling, structural analysis, check design performance, design okay, optimize not, so otherwise you keep repeating. And frankly speaking, you can never optimize something completely, it's impossible, right? Because so many things of the optimization, I don't even want to talk about the optimization here, but practically speaking, pure optimization or perfect optimization is not possible, not practical, right? So we look at a certain global optimization level that we can accept. But every solution has room to improve. But when you improve it in one area, it becomes bad in another area. For example, just to continue this discussion, is very important. Column size, right? You're trying to find the column size or the optimum column size or the best column size. Obviously, ground floor, if it's a 50-story building, ground floor column has the highest weight. So you need a certain size. After 10 floors, the load is reduced, so you need another size. So another 10 floors, every floor, the load is reducing, and you can theoretically keep changing the column size as you go up, right? That will be optimum design from the point of the calculation of this one. But almost no tall building does that. Why? Because the contractor has to make formwork every 10 floors. Everything has to be changed, and it becomes uneconomical on that side. So your optimum solution, which looks very good on one side, becomes unoptimum, and the window sizes have to be changed, the cladding system has to be changed, fixing has to be changed, everything has to be changed when you change the column size, and nobody likes that. They want quick construction, straight. So you end up having a highly non-optimized column, but an overall optimized building. So optimization of the structural system may not be the same as optimization of the whole building. So your decisions that you think are very genius may be very bad for the building, right? That's why we have to look at the bigger picture in that case. So you can change reinforcement. So what do we do then? We keep the size same, but we change concrete strength, very high strength in the lower floors. As we go up, instead of changing the size, we reduce concrete strength and reinforcement ratio. So we end up with a good optimized solution, but not the size optimization. Strength, concrete strength, and reinforcement quantity and reinforcement strength can also be changed. So you obtain economy through other means, right? And that is where the tall building design is different, that you don't think only about the sizes. You also think about the material strength that you're going to use. So for lower columns, very high strength concrete, the most high strength concrete your country can produce should be in the lower columns. The maximum possible, theoretically, practically, that you can get, you should use that concrete strength on lower floors. Then as you go up, then you get the size. And then as you go up, keep the size same, reduce concrete strength every few floors. Then you save money in concrete. Put the maximum reinforcement at the bottom and gradually keep reducing as you go up. So that way you can get some optimization without changing the other things. So preliminary sizing depends on not only finding the right size, but also finding the right material strength to be used. In China, what they do is that they not only start with a column at the ground floor, which has the highest concrete strength and highest reinforcement, they also put a steel column inside, make it composite. And gradually they take it out as they go up. So they make a composite column with steel section, high section, so it's a steel column inside a concrete column with reinforcement, with high strength, everything they can put. So the column size will be small, right? And then as they go up, they keep taking things out and they go up, right? Now, why is column size so critical? Saleable area. If your column is too big, you are reducing the area that they can sell. And the sellable area of a tall building in Bangkok, let's say, price is, what do you think? What is the price of 1 square meter area in a tall building apartment or office? 100,000 baht is typically the selling price of 1 square meter of space in Bangkok. So that means one square meter, about size of this table, is 100,000 baht. So if your column is 1 meter by 1 meter, you are losing 100,000 baht for that person per floor, not one time, 50 times. So if you made a column too big, you lost the client the opportunity to sell that area 50 times, which will 500,000, 100,000 multiplied by 50, 5 million baht straight away gone because you made the column too big. One column, there are 30 columns in the building. So your cost optimization, the client is ready to pay, put a steel section inside which will cost nothing to reduce the column area. Same is the case with shear walls, right? So structural parts have to be really reduced, vertical parts especially, so that the sellable area, net usable area, can be increased. Okay? So you target for highest possible strength of concrete and steel, maximum, and then you target for smallest column size, the ground floor, and that's how you go up. Okay? That's the rule for preliminary sizing of columns in a tall building. Same rule applies to shear walls. Sometimes in a building we want to increase the shear wall. The shear wall is coming out to be, let's say, 1 meter thick, and we want to increase it 1.1 meter. We cannot. Nobody will allow that. They will say, put steel plate inside, do whatever you like. We will not let you increase the wall thickness even by 10 centimeters because it will eat up a lot of space. Now, the span length in the floor system governs the floor system, right? And again, the argument, what I told you, applies. Minimum columns, because every time you put a column there, it heats up the floor area. So the client is ready to pay for an expensive floor, long span, rather than many columns. So instead of, let's say in a normal building, if the grade column spacing is 6 meters, which is quite common in most buildings, tall building, they will prefer it to be 12 meters or 11 meters, right? Most of the buildings that you see these days, their design is like this. There is a central core and there is only one row of columns outside, in between no columns. So that space is typically 12 meters or 13 meters, right? So that means you need to find a flooring system which can span 10, 11, 10 is typical, up to 12 is 12 meter is quite a lot of space, right? So you need to span that much. So you need to find a system which will be suitable for 12 meter. That's where post tensioning comes in, because it helps you to span longer spans. So you have challenges on the floor system because the spacing of the column is too big, and you have challenges then to column size because they want the minimum column size. So they only want the columns outside the building, not inside, right? So these are some of the rules. I don't want to go into too much. You can read this one about how to find the cost, the size of a typical column. Most of it what I've already talked about. Some applies to tall building, some is general. These are some of the rules. For example, deeper member also affect mechanical architectural cost and increase the floor height. This is an important thing to note here. So if your floor system is going to increase the floor height, now you see everything is opposite to each other. They want longer spans, smaller floor height, smaller column, taller building. So they want everything which is counter logical. It's not logical, but that's the challenge. Okay. So now what they want is they want long span, but they don't want to increase the depth of the beam, because if you increase the depth of the beam, let's say 15 centimeter in one floor, 50 floors multiplied by 15 centimeter, how much is that? 15 multiplied, okay, let's say 10 centimeter. 10 centimeter multiplied by 50, 5 meters, right? No. Yeah, so that's 5 meters. 5 meters is equal to 2 floors. That means you are eating up 2 floors of the building by increasing the height of the girder by 10 centimeter. And each floor they can earn 100,000 baht per square meter. So if there is a restriction in the building that you cannot make a building more than 100 meters, normally the height is restricted. So if you make the floor height smaller, they can add one more floor or 2 more floors and make more money. So they don't care about your beam, they want no beams if possible. That's why flat slabs are there. So if you put a flat slab instead of a beam let's say is going to be for 12 meter, typically the beam will be about 1 meter or 80 centimeter deep. A flat slab will be 250 millimeter. So you take out the beam from there, you reduce about 30-40 centimeters per floor multiplied by 50. You give them opportunity to add 4 floors. Multiply by 100,000 baht per square meter, right? 500,000 baht per square meter, they earn more from their building. So you are irrelevant to them. You know, your problems are not their problems. You are creating problems for them by asking for bigger beams, bigger columns, bigger things. So mentality has to be changed, tall buildings, because everything is a game of number of floors, floor area, sellable floor area, right? So priorities for structural system selection change. What you will do normally in a small building does not work in a tall building, and that's something that you need to remember. Column sizes, column arrangement, other things, these are important, but for, as I said, typically for tall buildings, the columns, we try to keep them square or invisible, right, on the outer side somewhere. And there's so many options, on this one. You go along. So the floor framing is usually about 20% of the structural weight, right? So we have to optimize it, maybe sometimes more. Span to depth ratio, spacing of beams, slab thickness, composite design, openings for mechanical ductwork should be carefully considered. So these are the things that you need to consider. These are some other concepts that will come in. I will show you pictures, I will show you things after that, but you need to understand one important concept, especially in tall buildings, the shear lag effect. shear lag effect. Shear lag effect is that when the building, tall building bends, the deformation from one side to the other side are not linearly distributed. They lose some flexibility in between. There's a flexibility of the framing system. So from this side to this side, you do not get a straight bending as you would in a solid cantilever building because of the shear deformation of the beams and slabs and other things that connect this face to that face. So that shear lag effect is quite important in most of the structural systems that we will be discussing. And because of that shear lag effect, building deformations become larger than they should be. Because of that, the vibration or the initial period become larger than they should be, and the force distribution in floor system becomes larger than they should be. So shear lag effect is something that we need to understand. And we get new terms, spandrels, that we will explain. So I'm going to show all of this to you later. Transfer beams and steel, use of steel, yeah, right? So we can come back to this after we have seen a few diagrams of the things. So simplified modeling. How can we do a quick modeling, simplified modeling, to do a back of the envelope calculation, right? So these kind of models are based on those things that you can do quickly by hand without running to the computer, because computer modeling takes a lot of time. Computers are supposed to be faster, yes, after we have created the model, but the modeling takes a lot of time, right? So stick model, quite popular, this one. Sandwich beam model, cantilever tube model, shear flexion model, reduced order continuum model, these are all getting complex. This is the easiest one. Stick model, you think of the building as just a stick. Forget about that there are columns in there, forget about that there are shear walls in there, because it's so long, so tall, that actually it's really a stick. And forget about the internal configuration of the stick for a minute, and you treat the whole building as a stick, as if it's a single stick, and then you do the calculation for that stick, total bending moment, total shear, right? As if there is no column inside, there's no shear wall inside. And based on those total forces, then you size various things. So don't worry about calculating the forces in individual members, because you may not even know those individual members yet. You'd rather do a calculation of the stick of the building and get the forces. Total weight of the building, total bending moment from the wind force, total bending moment from earthquake, and estimate what the mass per unit length will be, right? After that, you have those forces, then at each floor level, you can find what do I need to resist those forces. It's just like taking a column, single column, putting a horizontal load there, calculating the bending moment, and finding out how much reinforcement you need. So individual bar you can assume as a column, right? And the rest of the concrete as your floor. So you can use that concept of the stick, and then you can just get total effective flange, and after you consider that stick to be hollow or solid, equivalent solid or equivalent hollow, either way. So it requires a little bit of conceptual thinking. But once you get it right, it's so quick and often very reliable. In fact, the first computer software, ETABS, when it came up, initial models, was simply analysis of a stick model, because they used the concept of the rigid floor diaphragm, and there were only 3 degrees of freedom per floor. So if the building is 30-story, there are only 90 degrees of freedom. Nothing. And they would solve it like this, because there is no memory. But the point is that they considered at that time, even if you model the whole building, it is analyzed as a stick. One, they assume that each floor can only move in 3 directions. So only 3 degrees of freedom. A simple beam has 6 degrees of freedom. So basically we really reduced it to a very simple model, even in computers. Second one is sandwich beam model, right? So basically you assume that there is a beam with many components. It's a sandwich of various components. Then cantilever tube model, which is something like this. Shear flashing interaction model, which is including the shear lag effect that we talked about, and then reduced order continuum. This is a little bit more complex, so we don't. Actually, out of these, any worthwhile model is this one and this one. The others still require you more work. ACI came up with this nice guide to simplify design for reinforced concrete buildings. Unfortunately, not for tall buildings. So this is a very good guide, but it will work for low-rise buildings. Not many of the things that they discuss may not work for tall buildings, but anyway, as engineers, you'll be designing everything. So if you want to design buildings, there's a guideline who helps us to design, carry out the preliminary design of buildings. Cost-sensitive design. Very quickly, I will not spend too much time on it. We've talked about it. That cost is going to be an important thing, but we need to understand what is cost, right? And where is the cost saving that can be done? And we should not be saving cost in the wrong places. So we have to just make sure that look at the cost, and also remember cost has so many levels: financial cost, planning cost, intersection cost, maintenance cost, incidental cost, liquidated cost, opportunity cost, environmental cost, so many costs. For example, the cost of getting a loan to build a building and paying the interest is far higher sometimes than other things, right? So, for example, if you make a building and it's delayed, your loan is, your income is delayed by 1 year, right? You put up a structural system which takes longer to build. That means the contractor has to, or the owner has to wait 1 more year before he can get an income and pay back. So the interest of 1 year on $10 million that he borrowed will be far more than anything that you can save him, right? So the big picture is very important. So even if you spend more on a structural system and you can prove that you can make it faster and he can save on his interest, then you can justify your spending. But you need to know these things before you can talk to the client about this. Similarly, other things. So just be sure, be aware that cost is not just what you're making. Cost is a big issue. This is a typical breakdown: planning and design cost, direct construction cost, supervision and maintenance cost of a building project. Within that, architectural design is that much, site development is that much, structural shell. So it gives you an idea where the cost of the building is going. You can see planning and design cost, you people guys get nothing. Architect takes all the money, right? You'll be lucky even if you get 20%, right? If you work for the architect, you'll probably get nothing. So, but this is just to give you an idea where so you can see from here that this one, structural shell, is only about 25 to 40%. Architectural finishes are the one. So ultimately, if you can make an economic sense for your decisions to the owner, your decisions will be accepted. If you cannot make an economic sense to the owner, your decisions will not be valued. Right? So this is all about the cost. The importance of spending money should be demonstrated, or you should be able to defend it. So this is just to give you an idea within the building that how much percent goes to concrete, steel, how much percent goes to this one. This will give you a very good idea of where the cost of the building is. You can see, interestingly, that if you make a concrete column or beam, steel, concrete and formwork nearly have equal cost. And often we forget that. We often forget the cost of formwork. So the formwork cost is substantial, almost 25% of the cost of the member, which is temporary, which just goes away. So if you can make a design which can reduce the formwork cost alone, your design becomes more economical. You don't have to design, you don't have to reduce column, steel and concrete. Reduce the formwork cost, right? So we should know where the cost is going and we design accordingly and then make our designs acceptable. This is again a little bit of the details about the element, one particular element, what is going on into that element. It's difficult to read on this slide. Optimization, you talked about optimization of the cost, and just remember, cost optimization, cost consciousness, cost east, cost low cost has many terms, and each term has a very different meaning. But ultimately, what we are looking at is this curve. Oh, sorry, last two slides on cost. This curve. This is the curve of the optimum solution, right? Whatever you are doing in anything, at some point in that variable range, whatever you're looking for, it will be uneconomical. Once you change that variable, the performance or cost or whatever you're talking about will become low until the slope becomes 0 and then it will start to rise again, right? So we are looking for this point in the, for example, to give you an idea, make it clear, concrete column, again coming back to the column because it's easy. You have concrete there, you have reinforcement there, you have formwork there, right? If you make the column bigger, you need less steel, right? So the cost of the steel will come down, but the cost of concrete will go up and the cost of formwork will go up, right? If you reduce the column size, the concrete but steel will go up. So there is going to be a balance somewhere in which the formwork and concrete and steel, they will all have the minimum balance side, and after that, even if you go this way or that way, cost will go up, right? So the column size which gives you the least cost of the formwork, this and concrete and steel at the same time is your optimum solution, right? So if you increase the size a little bit, steel may come down, but concrete and formwork may increase, so you become so it is possible to achieve an optimum column size for one floor, right? But as soon as we go to the next floor, same column size will not be optimum anymore because loading has changed, right? But then we still keep it the same because now we are looking at not optimization of one floor, we are looking at optimization of the whole column along the height. So other factors come in. So a solution which is optimum for one member is not optimum for a set of members. And a solution which is optimum for a set of members is not optimum for the whole building construction. And a solution which is optimum for the whole building construction may not be optimum for the whole system, which includes other things also. And a solution which is maybe very optimum for the whole building solution may not be optimum for the long-term maintenance of the building, right? So there is no single optimal solution that will optimize everything. That's why people use life cycle analysis to find the best solution, not of the construction today, what happened before, what will happen in the next 50 years, and what will happen when the building is demolished, right? So if you consider the whole life cycle optimization, and if you can optimize that, then it will be really good. But that invariably, almost always result in an unoptimized building to build with, right? Which the client will not accept because the client is paying for it. He doesn't care what happens to the building when it's sold, right? So he's not interested in the rest of the life cycle optimization. So typically a building that they design now, a tall building, is not an optimum solution for the life cycle, because the people who made it have only a short-term view, right? So anyway, this is a whole idea. So when you design something, you should at least know that what you're doing has a very long time impact. And also optimization levels, micro level, local level, global level, universal level. So you should see what are you trying to optimize. And a lot of engineers spend too much time here. They don't see that side. Now we come to the interesting, important concept related to the planeway design, which is the premium for height. What does it mean, premium for height? What do you understand by this term? How much I have to pay, or you have to pay, to make the building taller? Not in terms of money, but in everything. What is the cost of making buildings taller? Which also tries to answer the question, how tall I can go, right? In another way. So we are trying to see, are we paying too much to make a tall building? Is it justifiable? So we should be able to separate, like I said in the beginning, the cost of just only designing for gravity loads and designing for lateral load because of the height of the building. And this discussion is here. Concept of premium for height. Now please look at this graph and try to see what we are saying. This is the floor framing, which is constant, right? Every floor, we assume it is designed for its own gravity. It doesn't matter whether you have 10 floors, 1 floor, 100 floors. The cost of one floor framing, we assume, remains the same because we are not linking it with anything else, right? This is the increase in the cost of the columns as you go up, right? Because the load is added, so as you go up, the premium for height will keep increasing. For 0 story, there's no load, but as we go up, this will be keep adding, and this graph will linearly increase. So if you have 10 story, column load is 100, 20 stories 200, 30 stories 300, because it's simply number of floors being added. So this will go like this, like a linear, so that's fine. Problem is here. The lateral bracing or lateral system that you need to resist the lateral load, that increases by a curve of higher order, not linear. So you cannot say that from 10 stories I have a certain cost, for 20 stories the cost will be double. No, it will be maybe 2.5 times. Another one 3 times or 4 times, and so on. So every 10 stories will add higher multiplier for cost as you go up. Why is that? This is only for weight. Earthquake will be even worse. Yes. First of all, why is this like this? The equation of the wind pressure is velocity square kind of thing, right? And velocity is increasing as you go up. So when the velocity is increasing and the force is increasing, pressure is increasing by velocity square. So definitely the forces are increasing, not straight line, but they're going like this. So if the forces are increasing like this, your lateral system will have to be increased like that. So that means after some time this curve will just become too much to handle, right? So this premium of height for height, and you can see from here, structural steel pounds per square foot for typical building, let's say for gravity it was 8, for column when we do it becomes 20, and for lateral it becomes 50, right? So huge premium we have to pay for height. That is why you see all these tall buildings reducing height at the top, because as the wind pressure is increasing, they are reducing the area exposed to wind, trying to keep the forces straight and trying to avoid this curve and trying to make it linear so they can go higher, right? So that is one way to beat this curve, is to reduce, this is assumed straight height. So if you reduce the height in the same proportion that the wind is increasing, you end up with a straight line increase, which gives you less premium and you can go taller, right? So this is using conventional system. There are other ways to prevent this from happening, right? Tubular system, for example, does not follow this law, right? That follows another law, and that's another way to handle this problem. And people combine now reducing the height and also using tubes, so they get double advantage, and that's why 800 meter or 1 kilometer tall buildings are possible, which were not even thinkable a few years ago. So, in concrete construction, major factors responsible for reducing reinforcement in concrete quantities are: number one, new framing techniques such as skip joint construction. That means you reduce the connections between columns and beams. You skip alternate connection, make them longer, or so column, instead of connecting the columns every floor, because every time you have a connection, you have splices, you have joint reinforcement, you have so much cost. So if you avoid connections, then you don't need. See, the interesting thing is, the column in a tall building is at least 1 meter by 1 meter minimum, a typical tall building, and it's only going 3 floors high. You don't need to have a joint. It doesn't need a joint there. It doesn't need a bracing. This column can easily go 5-6 meters without any problem. So if you put a floor in between, you're simply adding to the cost a lot. So if you can skip that and connect every other floor, right, then it's good. And so what people do is, structural floor height is 2 floors, and then they hang 1 floor from the other floors later. Recast or whatever, even the cast in place floors, they can come and build later. It makes it easier. Instead of making every floor, you make a floor every 2 floors and leave 1 floor blank and come and make it in another lighter system and hang it up, or so you don't need a joint, or put it on a corbel. So your main structural system is 2 floors high or 3 floors high, and that's what you make. And then you come back and then you hang floors or make the other floors only 2 floors high, supported by these primary floors. So you create a composite system in which you have a building with a floor height of 9 meters, but the column is good enough for 9 meters, it's not a problem. And then you say, okay, after that I'm making 2 floors like intermediate floor on a real floor, right? So those kind of things really reduce the cost and weight of the framing and other things. Increased use of mechanical couplers for instead of using web splices, you use mechanical connections between rebars, because you waste a lot of reinforcement by overlaps, splices. So you don't use that. You bring the concrete big bars together, put a mechanical coupler between them, so you reduce cost. Things like that. Use a wide cage for column ties and so on. So use of high strength concrete, use of lightweight aggregate. All of these things can help you save the cost in a concrete structure. So, point is, think outside what you know, right? Why does that floor have to be 3 meters every floor? Yes. So, also design a system in which the glass curtain can be reduced. So that has a lot of weight. So this is another way of the same graph put in this way. So this is very interesting. Now if you put the reinforcement like this, or you put the reinforcement like this, or you put the reinforcement like this, it changes the performance, does not change the cost. So just rearranging the reinforcement can give you benefits because you just know where it is needed. For example, A is here, B is here, and C is here, A is here. So basically what you can do is you can increase the performance by simply rearranging the bars to where they are more effective, right? So you get higher performance for the same cost, right? Or in other words, another way, you can get the same cost as A with the reinforcement which is optimized in such a way that you use larger bars and more bars, fewer bars, but ultimately what you need is you do not need the bars in the middle. They are not effective, right? So if you can increase the spacing with larger bars and fewer bars, you can get almost the same capacity as that one, right? Or you can get a higher capacity and reduce the cost, right? So this is lower cost, the same performance. This is the same cost with higher performance, and this is the best one. So these small things can help you to optimize the design. All right? Any questions?